This is the last exam in the class before the final, and it's going to be over integrals. So the idea behind this section is we have a new saying. Before I said derivative, and then you said rate of change, or if I said rate of change, you said derivative. Now, if I say integral, you're going to say area. And if I say area, you say integral. So it's real simple. These are the two, basically calculus is composed of two parts, a differential part and an integral part. The differential, which is the derivative, studies the rate of change, and we try to understand how the rate of change can be used to say things about a function. And the second part involves this integral here, and we use it to find the area, or to understand the idea of area, and specifically the area underneath the curve. So if I give you a function f of x, one question we may be interested in, and you'll see why later, so there's my f of x, which is poorly written, but there it is, and you may be interested in the area underneath this curve between a and b. And what the integral will do is it will tell us this area. So we're going to break this up into several different parts. This week we're going to cover definite integrals and area, part 1 and part 2. I'm not sure if we'll get to indefinite integrals this week, but definitely next week we'll do indefinite integrals. And these are really sort of two different questions, but yet they're connected, and they're connected by this fundamental theorem of calculus. We'll talk about this, and then we'll talk about one technique of integration. So there'll be some integrals we can do rather easily. And there'll be some that are a little bit more difficult to do, so we'll have to apply certain techniques to them. So we'll do one technique, integration by substitution, and in Calc 2 you'll learn all the other techniques of integration. And then we'll end here with the fundamental theorem of calculus, and we'll call this part 2, and we'll actually discover how integrals can be used to discover new functions that cannot be made out of those elementary functions, you know, the power functions, exponential functions, logarithmic functions, and trigonometric functions. Most of the functions we've worked with up until this point could be made by adding, subtracting, multiplying, dividing, or composing those four functions. Well, we'll discover that there are actually new functions out there that are not elementary, that cannot be built from those elementary functions, and they rise from this integral. All right, so that's just a brief introduction. Let's get to what we're going to do tomorrow in class. So tomorrow in class, we're going to talk about this definite integral and the area. So what is the definite integral? So let me do some notation for you first. So normally, when you see the integral, you see this elongated s, which is what it is, and then you have some numbers here, a, b, and then you have some function f of x dx. As an example, what we're going to do today is we're going to do the integral from 0 to 10 of x squared dx. So this is a typical integral. Now each part of this integral has a name, so let me sort of name these things. So a and b are what are called limits of integration. And so a and b, these are the limits of integration. And then this f of x is sometimes called the integrand. And then this whole thing is said, when you write this expression down, we say this the integral from a to b of f of x dx. And you can see the parts here. It's kind of obvious, right? So the integral sign, let's use green. So the integral, when I see that, it really corresponds to this elongated s. And then from a to b, of course, we've already highlighted those with yellow. So, you know, from a to b, it means from a to b. And then of f of x, we put in red. So let's just, you know, of f of x. And of course, the dx on the end is right here. And so dx. So the integral from a to b of f of x dx. So over here we have the integral from 0 to 10 of x squared dx. And what does this mean? So probably the most important thing to understand is when I say integral, you should automatically think what? And hopefully you remember from the last slide there, area. So I say integral, you say area. I say area, you say integral. Right, these are basically these two things are basically the same. And when we solve a problem, a lot of times we'll use this sort of statement to help us solve it. You know, we'll be doing an integral, and I'll say, okay, I say integral, you say area, and then you'll realize, oh, or if you're trying to find the area, I'll say area, you'll say integral, and you'll realize I need to use the integral to solve this problem. So what this really represents, so this is just a bunch of symbols over here. So what does it really mean? Well, there's really sort of a picture that goes with this. And here's my function, f of x. And the idea is that if I go from a to b, and I want to find this area, I can represent this area here, and let's call this A. I can represent this area A, and that's exactly what this thing is. Right? This is the area A. Right? So this is just is equal to the area underneath the curve from A to B. Again, real simple. I say integral, you say area. I say area, you say integral. Right, so it's just a bunch of symbols, and what the symbols represent, these represent basically where you're looking from. So like in this example above here, what I'm looking at is between 0 and 10, and then this is my curve, my function, and if you graph x squared, on the right-hand side, I mean, it's a parabola, so it looks something like this. And suppose 10 is here and actually goes up on this side too, right? And there's 0. What this thing actually represents is the area underneath the curve, f of x equal x squared, between 0 and that's a 10. And 0 and 10. And so that expression means that stuff right there. And this is not too difficult to understand the idea behind. You have a bunch of seemingly random symbols placed in certain spots, and then it means a certain thing. I always tell students, you know, here's a nice looking word that nobody has a problem with, D-O-G, dog, but there's no hair on D or O or G, and there's no ears, and there's no slobbery tongue. Right, it's just D-O-G, dog, a bunch of seemingly random symbols, but when we look at it, we immediately recognize all the different dogs in some sense that we've seen. So when you see this, you just need to immediately recognize that that's the area underneath the curve between A and B. Okay, so we talked about the notation. I explained how it's connected to the area. Now, how can we estimate this area? So now think about this. Here's the picture right here, and we want to try to understand, you know, how can we estimate area? So suppose for some reason I want to find this area underneath the curve. How can we estimate area? And if you think about it, the answer is actually real simple. You basically know how to find the area of basically one thing, and that's a rectangle. You know a rectangle is length times width when you're finding the area. And so the idea is, can you estimate the area by using rectangles? And hopefully you say, oh yeah, I can kind of see how you could do that. I could take a little rectangle here and figure out its area. And it's going to be close to the area right here, but it's going to be a little bit off. You see there's a little region here. But then I could take another rectangle and another rectangle and another rectangle and so on until I filled up this whole space with these little rectangles. And so here I took 1, 2, 3, 4, 5, 6 rectangles, and I can compute these areas because I can measure the length here and the width, or let's call this the height, since we always refer to the height of the function. So the length and the height here, and I can figure out the area of this one, this one, this one, this one, this one, and add them all up. Now, how can I get a better approximation to the area? And hopefully you say, well, take more rectangles. All right, so I could take more rectangles, make them smaller, and so on. And the smaller you make them, the better approximation to the area you're going to get, and so on. I can keep on doing this until I have almost an infinite number of rectangles, and that's really the idea. You take more and more rectangles and see what happens as you go to infinity. As you take the rectangles more and more, what happens to this number that you're adding up, these areas you're adding up. And that's the idea. So we're going to do this, and we're going to do it in 3 different ways. We're going to do it with the left-hand sum, the right-hand sum, and the midpoint sum. And I'm going to walk through each of these. Oh, and then we'll do it with technology, of course, your calculator. All right, so let's take a look at the first example. And we want to use the left-hand, I guess I put rule on here. It doesn't matter. Left-hand sum, left-hand rule, they're really the same thing. Some books like to call it the rule. Some like to call it the sum. And so it says estimate the area underneath the curve with the left-hand sum. All right, so let's first draw a picture, and if you don't know what this looks like, I already drew a picture of this, but pretend like you didn't. If you did not know, you could use your calculator, and you could graph this because you have a graphing calculator. So on my calculator, let's go to y equals, and let's clear this out, and let's graph this thing, x raised to the 2. And I care about my window goes from 0 to 10. So 0, enter, 10, enter. And then I'm going to zoom fit it. So here's my zoom fit. And I should get a nice looking graph. All right, so it looks something like this. Just copy it down. And I already knew this, but you can always use that calculator. So 0 to 10. And this n equals 5. N is actually the number of rectangles you want to take. So this is just the number of rectangles. That's how I think of this. You can also think about it as, you can actually give a definition for this. N is equal to b minus a. Oops. Let me trace this back. You'll see later that the change in x, delta x, is actually equal to b minus a over n. This is something you can store in your memory if you like, but you really don't need it. The best thing to remember, I think, is that n is just the number of rectangles we're going to take. So if n is equal to 5, how many rectangles do we want to use? And hopefully you say 5. And so we want to estimate this area underneath this curve. So I want to try to figure out, what is this area right here, right all the way up to. And so I'm trying to figure out, and I'm going to use what's called the left-hand sum. And I'm trying to figure out this integral, a, which is equal to the integral from 0 to 10 of x squared dx. So copy this down. It'll help you sort of recognize the area when you see these symbols. So I'm going from 0 to 10. I'm trying to find this area in black, a. And what we're going to do is this left-hand sum. And I can write down here a is approximately. And so you want to make 5 rectangles, and if you have the left-hand sum, it means you want to start at the left endpoint. So let's do this in blue. So how do I break 10 into 5 equal pieces if I want 5 rectangles? And hopefully you think for a minute and you say, oh, I just break it into 2s, right? Because I can do 2, 4, 6, 8, and 10. And so I'm going to have 5 rectangles, one here, one there, one there, one there, and one there. And I'm going to start at the left endpoint. So the idea is I start here on the left and it has height 0, so that rectangle has height 0. If I plug in 2, remember, this is the function x squared. So if you plug in 2, you get 2 squared, which is height 4. So that's my next rectangle. If you plug in 4, you get 4 squared, which is 16. Again, I'm starting at the left. So that's 16. Make sure it looks like a 6. So 16. And if I plug in 6, I'm going to get 36. So the height is 36. And if you plug in 8, you're going to get 64. Great. Just like that. All right, so that's the left hand. This is going to be for the left-hand sum. And the idea is you take all these areas in blue, and then you're going to add them all up. And it's going to be approximately the area in black. And so you start with your first one, and we can even just write these down. So what I'm going to have is I have f of 0 times, and then my length here is 2. And you can see here over how I wrote delta x. You can always rely on formulas in the end, but remember, you always forget formulas. So 10 minus 0 divided by 5 is equal to 2. All All right, so yes, I have f of 0 times 2, which is my change in x here, plus then I have f of 2. So I'm just writing this down. You can actually skip this step if you want, but I want you to see it. Then I do f of 6 times 2 plus f of 8 times 2. And I already figured out these heights by simply plugging into my function f of x equals x squared. So this is going to be equal to then 4 times, oops, not 4, 0 times 2 plus, and then I have 4 times 2 plus 36 times 2 plus a 64 times 2. And I can crunch this on my calculator. And the way I would do this on my calculator is I would probably just do 0 plus 4 plus 16 plus 36 plus 64. Oh, and I just realized I missed a number. All right, plus 64. And I'll fix that in a minute. So that's 120, and then I'd multiply it all by 2. So I get 240 units squared. So I have 240 units squared. Let me get rid of that. And I forgot the 16 here. So let me put that in there too. So you should have right here, you should insert plus f of 4 times 2. All right. So insert that right here. And so down here, I'm just going to erase it down here. So down here I should have right there. This should be plus 16 times 2 plus 36 times 2 plus a 64. And then above here, you should have plus f of 4 times 2. And then we already have the plus, so I guess I don't need to write this symbol here. You should have 5 terms. Why should you have 5 terms? Because you have 1, 2, 3, 4, 5 rectangles. So my estimate for the area would be 240 units squared. Very good. Let's look at the next one. So I changed this one just a little bit. We want to use what's called the right-hand rule, or the right-hand sum, to estimate the area underneath the curve. And on this one, I made n equal to 3. So you won't have 5 rectangles. You will have, hopefully you say, 3 rectangles. And the reason I made n equal to 3 is if you think about it, it's not so easy to divide 0 to 10 into 3 parts. But we'll talk about it here, and it won't be too bad. So let's go from 0 to 10. Again, it's the same function. So it looks something like that. And we're trying to approximate this area. And this time we're going to do the right-hand sum. And so we're trying to find a. This a here, this area, which is equal to the integral from 0 to 10 of x squared dx. And so we'll come down here, and I'll write down a. And this is the right-hand sum, so let me just write down so you know the right-hand sum. And a is going to be approximately. Now I have to think a little bit. Okay, so how do I divide 10 into 3 pieces, into 3, because I want to make 3 rectangles? And if you think about this, the question itself answers itself, or the question itself is the answer. How do you divide 10 into 3 pieces? Well, if you can't see right away what that is, do something you can do. Right? How do you divide 10 into 2 pieces? And you automatically say 5. Right? So if you divide 10 into 2 pieces, you get back 5. If you divide 10 into, and you say, oh, 5 pieces, you get back, your brain says 2. Right? So now, think about what you're doing here. If you take 10 and divide it into 2 pieces, you get 5. If you take 10 and divide it into 5 pieces, you get 2. If you follow the same sort of procedure, if you take 10 and divide it into 3 pieces, how many pieces are you going to, in some sense, I mean, you get 3 pieces, right? But what are the lengths of these pieces? Because that's the length, length 5, length 2. And what you're doing, hopefully you see here, is you're actually just dividing. All right, so 10 over 3, the reason why you don't know it right ahead is because it's not nice. It's 10/3. And now understand how you did it before. So before we did this, we divided 10 into 5 pieces. And you realize it was, length 2 each time, so you just count it off. 2, 4, 6, 8, 10. You do the same thing here, but instead of counting by 2s, you're going to count by 10 over 3s. So you're going to go from 0 to 10 over 3. You're going to add another 10 over 3, and that's going to give you to 20 over 3. And then you're going to add another 10 over 3, which is going to give you to 30 over 3, which is just 10. So it's actually really simple if you think about it. In the question, when you say, how do you divide 10 in 3 pieces? Take 10 divided by 3. The question itself answers itself. All right, so once you know how to break up your interval into 3 pieces, and again, you could use the formula that you know that delta x, the change in your x. The delta x is really this distance from here to here. That's our delta x. This is equal to your b minus a divided by n. So I mean, you can memorize a formula if you like, and I don't mind that. I just don't think you'll ever remember it, and you have 3 pieces. So 10 over 3. I think it's better to understand n is 3 rectangles, and then how do you divide 10 into 3 pieces. There will be times in your life where you need to divide things up into pieces that are not nice. And so it's useful to know, how do you divide 10 into 3 pieces? 10 divided by 3. And we're going to use the right-hand sum here. So the idea is use this right endpoint. So this is going to be 10 over 3 squared. And we're going to do the right now, not the left. And 10 over 3 squared is 100 over 9. And then, I'm going to sneeze here, hon. Excuse me. All right. And now, again, we use the right endpoint and go up and over. And so this is 20 squared, which is 400 over 9. And then this is 10 squared. So again, right endpoints. The right-hand sum uses the right-hand side, the right endpoint. And this is just 100 because 10 squared is 100. And what we want to do is compute these areas. Now, you see you're not going to get a very good approximation because you have a lot of area on the outside. And that's obvious because how many rectangles did you use? You used 3. So it's going to be a terrible approximation to the area, but yet you can still use it as a approximation. So on this one, we're going to use f of 10 over 3 times. Now, my length is no longer 2 like in the last one. The length is now 10 over 3. So times 10 over 3 plus f of 20 over 3 times 10 over 3 plus f of 30 over 3, which is f of 10, times 10 over 3. And I've already figured these out. Remember, my function over here is f of x equal to x squared. So I just plug in this 10 over 3 into x squared, and I get this to be equal to 100 over 9 times 10 over 3 plus 400 over 9 times 10 over 3 plus, and I guess I could use this. This was 30 over 3, so this is going to be, what, 900 over 9 times 10 over 3? I mean, if I don't want to use a calculator, I can just do this pretty fast, right? This is going to be 1,000 plus 4,000, so that's 5,000 plus 9,000, so I'm going to have 14,000 on top, divided by, and then I have 27 on the bottom, right? Because 9 times 3 is 27, 27, 27, so 14,000 divided by 27, and this is units squared. So I'll go with this answer here. I'm not sure if it simplifies or not. I need a calculator to figure it out. And of course, you can use your calculator. So if you know it's 14,000 divided by 27, I can certainly hit that, and then I can hit my math button and fraction and convert it, and it doesn't simplify. I mean, I certainly could divide 14,000 by 3 and see if 3 goes into it, and if it doesn't, I'm done, right? Because 27 is 3 cubed. So 14,000 over 27 units cubed. Now, let's look at the number real fast. So the number I found is right here, 518. So it's approximately, let's just round, 519 units squared. And I want you to think about this number and how terrible of a approximation it is. So in the last problem, we found this to be what? Let's see. Up here, we found it to be 240 units squared, which is probably not a great estimate, but it's certainly a better estimate than what we found down here. And understand why. It's because we took fewer rectangles. We only took 3 here. So the idea is if you take more and more rectangles, you're going to get a better and better approximation to the area. And more, hopefully understand, as you take more, as you take 100, 1,000, 10,000, this is introducing the notion of a limit into the problem. And you'll see tomorrow, in tomorrow's lecture, how that works. Okay, last one. We're going to do it with what's called the midpoint rule. And so again, let me draw the function. And I brought n back to 5, so because this is just a new rule, so I'm not really we have 5 rectangles again, okay? So here we go from 0 to 10. And here's what, again, the graph looks like, something like this. And so this is my f of x equal to x squared. I'm trying to estimate this area underneath the curve. So how would I do this? And my brain says, let's try to use some rectangles. And so notation-wise, I say area, you say integral. So the integral from 0 to 10 of x squared dx. And we're going to use 5 rectangles again, which means breaking this up is real simple. We have 2, 4, 6, 8, and 10. And now we want to use what's called the midpoint rule. So the idea is find the midpoint. So let's find the midpoint here. And so the midpoint here is 1. And so if you plug in 1, you get a height 1. And so my rectangle here will have height 1. Here the midpoint, of course, is 3. So if you plug in 3, you're going to get out 9. So this will have height 9. Because again, I'm squaring my function. Here the midpoint is 5. So I'll put a 5 here. And if you do that, you're going to get out 25 for the height of my rectangle. And then here it's 6. So you start at 6. So the midpoint is 7. And so if you square 7, you're going to get out 49. So the height is 49. Go over a little bit more. And then here the midpoint is 9. If you square 9, you get out 81. And so there's my rectangle there. And you see I have 5 rectangles, and I'm using the midpoint because I'm using the midpoint rule. So understand the idea. The left-hand rule, use the left endpoint. The right-hand rule, use the right endpoint. And the midpoint rule, use the midpoint. And so I'm going to figure out the area of these rectangles, add them all up, and get an approximation for the area of A. So let's do that. I have A is approximately, and I can write down the formula if you like. So my delta x, again, is just equal to 2. But again, you can compute it if you really want to. B minus A over n. So this is 10 minus 0 over 5. And so it's equal to 2. Right? Again, that's just this distance from here to here. Right? 0 to 2. And so what I have is f of 1 times 2 plus, these are using the midpoints to plug in my function, f of 3 times 2. And I've already computed these, plus f of 5 times 2, and you should get 5 terms because you have 5 rectangles, f of 7 times 2, plus f of 9 times 2. All right. And then over here, this is then equal to what? Well, we plugged in 1 and got 1 squared, which is 1 times 2, plus this is 3 squared, so 9 times 2. This is 5 squared, so 25 times 2. And then plus 7 squared, so that's 49. 49 times 2. And then plus 9 squared, which is 81 times 2. And I'll use my calculator to crunch this number. So how do I get this? Well, I have, 1, and I just usually add these up. So 1 plus 4 plus 9. Oops. Here. Let's look at it because I can't see it. So I'm just kind of guessing at what these numbers are. So there's 1, 9, 25. So 1 plus 9 plus 25 plus 49 plus 81. So I should have 5 numbers there. And I'm multiplying all by 2. So I just add them up and multiply everything by 2. And I get my answer of 330 units squared. Perfect. All right, so 330 units squared. Okay, and so the last example we want to do is using a piece of technology. And so your calculator will do this for you. So again, draw the picture. I always draw this picture. That way you kind of know what you're actually doing. So you're going to go from 0 to 10. And actually, let me move it over here because we're going to use the calculator in the end to do this. So if I was to use the calculator, let's pretend like I haven't done this problem before. I would enter x raised to 2 into y equals. So hit y equals x raised to 2. I'll make my window like I did before, 0 to 10, and then zoom fit it. And when I zoom fit this, I can see the graph. So here's the graph. And so let me copy this down right here. 0 to 10. And the graph looks like this. This is the graph of f of x equal to x squared. And I'm trying to figure out what this area might be. So what is A? And so A is equal to the integral from 0 to 10 of x squared dx. And on my calculator, then I can figure this out. If you hit second trace, it pulls up the calculate menu, and then you know what to use. I mean, look at it. Which one do you use to compute the integral? And hopefully you say, oh, number 7. So you can scroll down here to number 7 and hit enter on it. And it's going to say lower limit and upper limit. Now your lower limit is 0, so you're going to hit 0, enter. And then your upper limit is 10. Right, so these are called limits of integration. So maybe I should point that out. 0 is the lower limit, and 10 is the upper limit, obviously, because 0 is on the bottom and 10's on the top. And so then you have a 10 here. We hit enter, and it's going to shade the region and spit back a number. So 333.33. So let's just round this to the nearest whole number. So 333 units squared. And that's a pretty good approximation. You could even do it to 2 or 3 or 4 decimal places if you like. But your calculator will do this for you. But now what is your calculator doing? You can almost see. You see those little tips? It's simply adding up what? Adding up little teeny tiny rectangles. So maybe it's doing like 1,000 or so of these little teeny tiny rectangles to get this 333.33 out. So your calculator can do the same thing we're doing, but it does not mind adding up thousands or 10,000s or hundreds of thousands of rectangles, whereas we do. We don't want to spend our time doing that.